Assalamu alaikum students. Welcome to lecture number 7 of your FM2 course. And in this lecture, we will be talking about flow or immersed bodies. And by immersed bodies, we mean that the bodies that are immersed in a certain type of fluid. That fluid can be air or that can be some type of liquid. So this is your chapter 9 from your Munson book. This is your chapter number 9 from your Munson book, and in this chapter we will be studying the various aspects of flow or bodies that are immersed in a fluid, and examples include air around an aeroplane, automobiles, falling snowflakes, or flow of water around submarine or fish. And in these situations the object is surrounded by the fluid and the flows are termed as external flows. So we will be looking at the geometry of our bodies and also the flow characteristics, and we will look at them both to see how different type of forces and pressure distribution and momentum etc. are affected by the both the body shape and the flow characteristics. So let's do that. So first, let's classify the shape of the bodies that will affect the flows or that we'll be considering in our analysis. So there are mainly three types, and the first type is two-dimensional, in which we only take the cross-section of our object or our body that is under consideration or that is immersed in the fluid. In the second type, the type is axisymmetric, and by axisymmetric, the cross-section is rotating around a certain axis to get the axisymmetric shape. As you can see, the cross-section of this object or this body will be somewhat like this in the form of a bullet. So if you rotate this along a certain axis, you will get a shape like this. So these are axisymmetric objects. And then the third type is the three-dimensional objects. So two-dimensional objects are those that are infinitely long and have a constant cross-sectional size and shape. So we will just consider that body as two-dimensional, and we will take the two-dimensional cross-section of that object if it specifies or if it classifies these conditions, if it is infinitely long and if it has a constant cross-sectional size and shape. Then the second is axisymmetric bodies, and they are formed by, as I said, rotating their cross-sectional shape about a axis of symmetry. And then the third is the three-dimensional bodies that may or may not possess a plane of symmetry. So such as this aeroplane, it does not have any line of symmetry, its cross-section is not constant throughout. So we will consider them as three-dimensional bodies and will do the analysis in the three-dimensional as such. And at the end, the flow characteristics are also dependent whether the body is streamlined or blunt. And we will look at these two examples in the coming slides. So by streamlined are those that do not affect the flow too much, and blunt are those bodies that affect the flow considerably. So as you can see, you can say that this this right here is streamlined and this right here is a bit blunt. So you also have an idea if you look at racing cars or Formula 1 cars, they are a bit streamlined to help them in gaining the required velocity and acceleration. And the blunt bodies, you can take the example of your trucks or your heavy duty vehicles that are not in streamlined shape. So those are the kind of blunt bodies. Then we will be considering ourselves with the forces that are acting on a body. So if we take any body that is immersed in a fluid, there will be two type of forces. One will be the pressure forces that will be normal to the body, and the other will be the shear forces that will be along the body, parallel to the body. As you can see in these two conditions, these are the pressure forces and they are normal to the surface of this object, and this is an aerofoil, as you know, airfoil. And in the second type, the shear forces will be along the object, along this aerofoil. So if we take these two forces and the resultant of these two forces, so the forces that are along the upstream velocity, this is the upstream velocity, the forces that are along the upstream velocity or parallel to this upstream velocity, they will be termed as the drag forces, and the forces that are normal to this upstream, they will be termed as lift forces. So as you can see, forces from the surrounding fluid on a two-dimensional object are pressure forces and viscous shear forces, and the resultant of these two forces we get lift and drag by finding the resultant of these viscous shear forces and the pressure forces. So what we will get a drag force that will be parallel to this upstream velocity and a lift force that will be normal to this upstream velocity. We find these two values, the lift and drag, by this coefficient. One is the lift coefficient, this is the lift coefficient, this is the lift coefficient, and then there is the drag coefficient. So we use these two values to find the lift and drag on a certain body, and this is the lift force. Then in the denominator is the density, velocity and area. Similarly, this is the drag force, and in the denominator is the same term as this. So these are the lift and drag coefficients used to find the lift and drag force, and again they are derived from experimental analysis, from empirical analysis. Here is a term that is in the denominator of these two equations is the area. So what will be the area? The area can be the frontal area in this case. In the frontal area, if we look at it in this direction, so we will get a projection. We will get a certain projection, and from that projection we will find the area of our body that is under consideration. One is the frontal area. So in this case, we will take the area of the frontal area, or if we look at from this direction and project in the take the projection of this cylinder on this plane, so what we will get, we will actually get the cylinder, we will actually get a rectangle, sorry, we will actually get this shape, rectangular shape, as you already are familiar from your drawing course, and the area of this will be A is equal to D into L. So this is the frontal area of this cylinder. Another type that is given below for these kind of shapes, the aerofoil that is given like this, we will take the plane form area. We will take the plane form area. So in this case, we will look from above. We will look from above, and whatever projection this object makes, so again it will make a rectangle, and we should know the chord length and the length of the aerofoil, so we can find the area as such. So this is how we are going to find our area that is required for finding our lift and drag force in the lift and drag coefficient formula. So we will again get the frontal and the plane form area for objects like these, and put it in these two equations to find our lift and drag coefficients, or our lift and drag forces. So again, the lift coefficients and the drag coefficients are dimensionless forms of lift and drag force. So these are dimensionless entities that are used to find the lift and drag force. Now, what we are interested in how the flow will behave when it moves past an object, and how will it be affected by the shape of the object, and how we can change the flow characteristics of a certain flow. So what we will do for a given size of a given shaped object, the characteristics of flow depend very strongly on various parameters such as size, orientation, speed, and fluid properties. So the size and orientation are related to the object, and the speed and the fluid properties are related to the fluid. So for external flows, the most important parameters are the following. One will be the Reynolds number. This is the Reynolds number, which is the ratio of inertial forces over the viscous forces. This is the Reynolds number. Then we have Mach number, and Mach number is the ratio of velocity of fluid divided by the velocity of sound. So this is the Mach number, and the third type is the most significant parameter is the Prandtl number, and the Prandtl number is again the ratio of the inertial forces over gravitational forces. So these are the three significant parameters, but we will be mainly focusing ourselves on the Reynolds number. We will be focusing ourselves on Reynolds number, and we will see that how by changing the Reynolds number past that is of a fluid that is flowing past a certain object, then we will see the flow characteristics when the Reynolds number is changed and the shape of the object is changed from streamlined to blunt and from blunt to streamlined. How will they behave respectively? So for a characteristic length of between 0.01 meter and 10 meter, and for a characteristic velocity of 0.01 meter per second, 200 meter per second, we will get our Reynolds number that will be between 10 and 10 raised to power 9. So for Reynolds number greater than 100, for Reynolds number that is greater than 100, we will have inertial effects. The inertial effects or the inertial forces will be dominant, and for a non-number that is less than 1, we will have the viscous forces that will be dominant. So this is the condition of the flow, because Reynolds number is related to the flow of the fluid, and it also depends on the geometry, because there is this length term, the characteristic length term, that is significant to the geometry of our object. So these are the two limits for the viscous forces and the inertial forces, and hence the most familiar external flows are dominated by inertia. Inertia, because normally we will get a Reynolds number greater than 100 for most of our flow conditions. So now what we will do, we will look at a streamlined body, and then we will look at the blunt body, and then we will change the Reynolds number of a flow that is flowing past the streamlined and blunt bodies, and then we will see how this flow behaves. So the general difference between small and large Reynolds number flow past streamlined and blunt objects can be illustrated by considering flow past two objects. So the streamlined object is a flat plate that will be parallel to the upstream velocity, and the other is a circular cylinder that will be our blunt object. So then we will see that by changing Reynolds number how the flow behaves. So let's look at some figures and see how the flow behaves and what can we see from that. In this case, this is the plate, this is the plate right here, and this plate has a certain length, and a certain fluid is passing through this plate with a upstream velocity of u, and the Reynolds number is 0.1. So we already said that if the Reynolds number is less than 1, then the viscous forces will be very dominant. So you can see that in this case, that this gray area represents the viscous effects of this fluid that are very dominant for Reynolds number that is 0.1. And then again the flow, the velocity in this region is u is less than 0.99 of the upstream velocity, and then the streamlines, as you can see, the streamlines are deflected considerably. There is a considerable deflection amongst the streamlines. So this is for Reynolds number 0.1 where the viscous effects are dominant, and the body is a streamlined flat plate, and you can see in the wake region you can also see the velocity profiles. You can understand these velocity profiles due to the no slip boundary condition. That's how the profiles will be made. This is for Reynolds number 0.1, and then let's look at the streamlines and the viscous region, the viscous effects and the velocity that is for Reynolds number 10. So the viscous, as the Reynolds number is increased, the viscous region is reduced to this much envelope now represents the viscous region, and the streamlines are not deflected as much as were they deflected in this case. And in this case the velocity in this region, in this gray region, is less than 0.99 of the upstream velocity, as was for this scenario. And in now for a Reynolds number is equal to 10, the viscosity is not that important as was for this Reynolds number 0.1. So now let's look at a very high Reynolds number regime, that is Reynolds number 10 to the power 7. You can see now that the streamlines are not deflected, very slightly deflected, and the viscous effects are very minimum, and now they are also in a wake region. There is a certain wake region in the downstream of this flat plate, and now there is a consider a very small viscous region, that is delta is very less than the length of this stream plate, this flat plate, sorry. So now for high Reynolds number, due to the 10 power 7, the inertial forces are now dominant, so the viscous envelope is reduced due to this high Reynolds number, and the streamlines are not very highly deflected as were in these two cases. So there is now also a wake region, a viscous wake region, due to this high Reynolds number, and the flow profiles, the velocity flow profiles, now you can see are more uniform. So you can also say that this is a very turbulent regime for this much higher Reynolds number, because the flow profiles are becoming more and more uniform. So this is how the flow will behave along a when it is passed along a streamline, or you can also say that how will the flow around a flat plate behave when the Reynolds number is changed from 0.1 to 10 to the power 7. So the main effect is on the viscous region, that the viscous envelope around this flat plate, and the viscous plates keeps on reducing when the Reynolds number is increased, and so the streamlines are not considerably deflected when the Reynolds number is increased. So this is for a flat plate that was a streamlined body. Now let's look at a blunt body and see how the flow behaves. So for a blunt body, we have taken a 2D cylinder, a two-dimensional cylinder, and for a Reynolds number again 0.1, this is how the flow will behave. There will be a viscous region in the upstream and both in the downstream of the cylinder. The streamlines will not be separated, but they will change their shape according to the body as such. So this is for a very low Reynolds number 0.1, where the viscous effects are maximum. Then we have a Reynolds number of 50, and for a Reynolds number of 50, now the viscous region is reduced, and the what happens is the flow separation occurs. Flow separations occur around this point, that is the point where the streamlines separate from this surface of the cylinder, and they form their recirculation zone. This will be the recirculation zone where the vortex generates, a sort of vortex or a separation bubble generates, and it also is a low pressure region, so it kind of increase the drag force. It will kind of increase the pressure difference between these 2 points. So it is an undesirable phenomena, but it happens at high Reynolds number, and as you can see in the upstream of this cylinder, the viscous envelope is reduced, and in the wake of this cylinder, the viscous effects are still dominant, and there is also a separation bubble that is occurring, the separation of streamlines across this 2D cylinder. Now let's look at a third scenario, and the third scenario is of a very high Reynolds number, that is 10 to the power 5, and in this high Reynolds number, the separation occurs right here, but it does not form a recirculation regime here. This is the recirculation region. This is the recirculation region. Recirculation region in the wake of this. This is the wake region of this cylinder. In the wake of the cylinder, here for Reynolds number 50, the recirculation regions form in the wake of this cylinder. But in this case, for Reynolds number 10 to the power 5, the boundary layer separates and it does not form a recirculation, but it separates, and it certainly, as you can see, flows very in unsteady manner in the wake region. So here, as you can see, the viscous envelope in the upstream of the cylinder is reduced to this much, and it is still dominant in the wake of this cylinder. So the boundary layer separations occur here, and this does not form any recirculation region, but it keeps on extending in the wake region. So this is how the flow around a blunt body will act, and this flow definitely changes by when we change the Reynolds number and when we keep on increasing. First, the viscous region that is in the upstream and in the downstream of this cylinder reduces to this for Reynolds number 50, and there is also another type of phenomena that is occurring, that is the recirculation region occurs, where the flow separates from this surface of this cylinder and forms a bubble, a separation bubble. But this is for Reynolds number 50. For higher Reynolds number, this bubble separation phenomena is reduced to a separated regions as such, and in the wake region there is very unsteady manner of these streamlines can be observed, and there is also a separation location of these streamlines, and it occurs in the wake of this cylinder. So this is how the flow around a blunt body will behave. We saw two scenarios, one was the plate and the other is a blunt body. So a flat plate was considered a streamlined object and a cylinder was considered a blunt object. Now let's discuss the boundary layer. You are already familiar with this term. We already discussed this in FM1, but let's look at this in detail. Because in the previous slide we discussed that a certain phenomena that was called the flow separation, that when the flow was flowing past a blunt body, that was the 2D cross section of a cylinder, the flow was separating in the wake of the cylinder, and that is an important phenomena in fluid dynamics because such phenomena gives us the lift and drag forces that are required, and in some scenarios they are unfavorable. So right now we are discussing boundary layer, and here again we are taking a plate. This is our plate, and there is a upstream velocity of fluid with an upstream velocity of u, or a free stream velocity, you can say upstream or free stream. We will call u as the free stream velocity. So u is the free stream velocity, and as this fluid approaches this plate, what will be formed? It will form a viscous layer. Yes, it will form a viscous layer, that is this layer, and inside this layer there will be our boundary layer. So as you can see from the name that it is the boundary layer is a layer near the boundary of our solid surface. So the plate is our solid surface, this is our solid surface, and this layer is our boundary layer. And inside the boundary layer you can see the velocity profile, that how it changes, that how this velocity profile changes as it moves along the length of this plate. And you are already familiar that why this velocity profile changes, because the no slip condition that we take near the boundary, due to the no slip condition. So due to this no slip condition, a certain velocity profile like this will be formed. So this velocity profile shows that the velocity near the boundary of the wall is 0, and as we move away from the wall, as we move away from the wall a certain distance delta, then the velocity approaches the free stream velocity. So if inside this boundary layer the velocity is u, so at this point below the above the boundary layer, u will be equal to small u will be equal to capital U, that is equal to the free stream velocity, and experimentally it is proven that u is equal to 99.99% of u. So that is above the boundary layer, that the velocity in the boundary layer becomes 99% of the free stream velocity as we move out of this boundary layer. But inside this boundary layer, the velocity will not be that of the free stream velocity, but due to the no slip condition, the velocity near the boundary will be zero, and as we move away from the boundary, a certain velocity profile will develop inside the boundary layer. So this is our definition of boundary layer, that it is a layer near the boundary of our solid surface, and in this boundary layer the viscous effects are dominant. As you can see, the viscous effects are dominant, and it is critical. This boundary layer is very critical in calculating our drag forces. This is very critical in calculating our drag forces. So whenever we are talking about streamlined bodies, or we are talking about blunt bodies, so this boundary layer is very significant. In terms of streamlined bodies, we are concerned with the lift. We are concerned with the lift, as we saw an example of a flat plate, or you can take an example of an aerofoil. As such. So these are streamlined bodies, and in this case we are concerned with the lift that is being generated. In blunt bodies we are concerned with the drag force. So this boundary layer phenomena is very important for studying these lift and drags for blunt and streamlined bodies. And again, this is in this boundary layer the viscous effects are dominant in this boundary layer, and due to this viscous effects the drag and the lift forces occur. So because if we take that this layer is, let's suppose, inviscid, then the lift and drag will not be occurring, but due to the viscous effects the lift and drag phenomena are occurring. So now let's now discuss the flow separation that we saw in the previous slide, and let's see how that flow separation occurs and how is this related to the boundary layer. So let's look at this diagram. Let's say that this is our solid surface. This right here is our solid surface. And as we move along this solid surface, let's have fluid with a free stream velocity of u, and let's say that fluid is air. If that air moves along this solid surface, then it will have a certain velocity profiles that will be generated due to the no slip condition along the surface. So as you can see in this case, normally the pressure does not change. If this is our pressure, then we say that the pressure is constant for both the upstream right here, that the pressure is constant here, right here the constant, there is also a constant pressure, and right here the pressure is not changing along the x direction. So that's why we get a boundary layer like this, that due to the no change in pressure in the upstream and in the downstream, the velocity profile or the boundary layer that we get near this surface will look like this. But as we move along this surface, then this boundary layer becomes steeper and steeper. As you can see right here, it becomes steeper and steeper. Now what is happening here, that the pressure is changing in the x direction. Here for the first case, let's say that this was the first case. Now in the second case, the pressure is changing as we move along this boundary right here. So now at this point for this boundary layer, for this second type boundary layer, at the upstream there will be a high pressure. And here there will be a low pressure. So that's why the velocity profile becomes steeper near the edge of this solid boundary. So again, as we move along further along this boundary layer, then we see this phenomena. Let's say that this is the phenomenon number 3. And now you can see that there is a certain reverse flow that is occurring, because here you can see that the flow is going forward, but it reverses right here. It reverses right here. This is where the recirculation or the flow separation occurs, and this is due to the pressure region, because here now at this point, at the upstream of this boundary layer, there is a low pressure. There is a low pressure right here. There is a low pressure right here, and here in the downstream there will be high. There will be high pressure. So due to this pressure gradient, at the upstream there is low pressure, and in the downstream there is high pressure. So due to this pressure gradient, the flow will reverse. The flow will reverse, as you can see from this velocity profile. The flow will reverse in this direction right here, and this is why the flow separation occurs as we move along a certain boundary, as we saw in the previous slide in cases of a blunt body. So due to boundary layer condition like this, the flow separation will occur, and the flow will separates, and it will again try to attach to this boundary, and it will form a recirculation region where the flow will try to attach to this boundary, this solid edge. So that's why the flow separations occur and the recirculation regions occur. So this is the phenomena of recirculation or flow separation that occurs for our boundary layers, due to our boundary layers. Now, as you can see, there are two types of boundary layers. One is laminar and one is turbulent. And as for this scenario, if we say that here the Reynolds number is a function of the length of this plate. If we say that Reynolds number is equal to rho u x divided by mu, and if we say that x is the length of this plate, this is this length of this plate. So as we move along this length of the plate, the Reynolds number will increase. It will increase in this direction. So if we move along this plate, the Reynolds number will increase, and ultimately it will the boundary layer will convert from laminar boundary layer to a turbulent boundary layer. And this transition occurs at exactly Reynolds number 5 into 10 raised to the power 5 approximately at this value of Reynolds number for external flow conditions, where the our solid or our body is a flat plate and the flow is external flow. The plate is immersed in a fluid, and for that purposes the transition is for Reynolds number 5 into 10 raised to the power 5. And as you remember, when we were talking about flow inside the pipes, so that transition was somewhat between 2000 and 4000. So below 2000 that was laminar, above 4000 that was turbulent. So that was in case of pipes, that was in case of flow inside the pipes. But for external flows where the body is immersed in the fluid, and in this case for a flow over a plate, a streamlined plate, then the transition between laminar boundary to turbulent boundary occurs at approximately this value of Reynolds number. So this is what I like you to note down, because what we noted for the transition of laminar to turbulent flow in case of pipes, that was very low values of Reynolds number, but for external flows these values are very high for in case of Reynolds number, and that is approximately in the region of 5 into 10 raised to the power 5. So now let's look at our previous diagrams that we discussed in the previous slide, and now let's see how the flow separation occurs and how that is a viscous phenomena. So in case of this, we saw this diagram previously, and now you can understand why the flow separation is occurring. If our boundary layer, let's say here our boundary layer is in the shape of this, and as it moves along this point, at this point we will get a reverse flow. We will get a reverse flow due to the low pressure gradient. So here this is the high pressure, this is the low pressure, and then there is this high pressure. So due to this low to high pressure gradient, a reverse flow will occur and the flow separates and it forms a separation bubble. It forms a separation bubble, and this separation bubble, this is also called a recirculation region. Recirculation region, because this recirculation region tries to attach back to this solid surface, so it forms a recirculation region, and sometimes this recirculation region travels in the wake of this cylinder, so it also forms a certain type of vortices. It also forms vortices, and these vortices also have certain amount of energy, so they in turn will apply some force on this cylinder. So this is again another fluid dynamics problem in which the vortices apply some force on the body that they are being formed from. So this is an undesirable phenomena, and sometimes failures occur due to this. We will discuss this more in depth when we are physically attending our class, and I will show you some videos. So this is again for Reynolds number 50, and please note that this flow separation phenomena and this recirculation phenomena occurs for laminar flows. This occurs for laminar flows. This recirculation and phenomena occur for laminar flows where the viscous forces are dominant. And we can also look at this example where the Reynolds number was very high, and as you can see the flow separation occurs, but it does not form the recirculation region in the wake. The layers actually travel along the wake, it does not recirculate. So this is for high Reynolds numbers where the viscous forces are not that dominant, and in the wake there are viscous effects, but those viscous effects does not force the separated streamlines to attach back to this cylinder. Because of the high momentum of the fluid, the streamlines actually travel along the wake in the downstream of this cylinder. So these are the scenarios in which the flow separation occurs, and from the boundary layer we can now comprehend that how that flow separation occurs due to this low to high pressure gradient, and due to this low to high pressure gradient the flow separates and forms a recirculation region for laminar flows, and for turbulent flows, for high Reynolds number flows, this recirculation does not form, but the streamlines actually travel unsteadily along the wake of this cylinder. So now let's look at another practical example. You can see that this is a sphere. This is a certain type of sphere. This right here is a sphere. And here you can see that this is the upstream velocity, and the streamlines will be formed like this. And right here the flow separates. The flow separates and form this recirculation region, and similarly for here, the flow here separates and form this recirculation region. So this is again that exact phenomena that here the pressure is high, here the pressure is high, and here the pressure is low. So due to this low pressure gradient, the boundary layer that will be formed will be in this direction, and due to this reverse flow profile of the velocity, the flow will separate and it will recirculate in the wake of this cylinder. So these are the certain fluid dynamic phenomena that are very important, and whenever we are talking about actually the viscous flows. And again I would like to repeat that if we like to have lift or drag, then we will talk about viscous flows, because in case of inviscid flows, we will not have lift and drag. But if we take a cylinder, in case of inviscid flow, then the flow will come right here. It will have a stagnation point, then it will travel along the cylinder. It will have another stagnation point right here, and it will flow like this. So the streamlines will look like this. In case of inviscid flows, the flow will not separate, but this flow separation phenomena is desirable in case of viscous flows, because it gives us lift and drag, and that these are the two forces that we are concerned about, and that's why we study the boundary layer, the boundary layer for the lift and drag forces. So hope this was clear, and then we'll discuss some videos in our next class.